is my pleasure today to introduce me. I'm going to be talking about planning algorithms applied to crowdsourcing. And just like to point out that there's a large number of students who've done the work that I'm actually talking about today, as well as colleagues James Lenday and Mausam at IIT Delhi, who've jointly supervised some of the students here. I want to start by putting the talk in context. And over the last 15 years, I've done a lot of work on what may seem like disparate topics. So there's a fair amount of work, especially with Christoph Gaius, on adaptive interfaces, work with Tessa Lau and Jinheng Chen on programming by demonstration, how to actually automate routine tasks and get computers to basically might be easier to use, and also quite a bit of work on information extraction, where the objective is to build a big knowledge base that can be used for answering questions. So the high-level theme that ties all of this stuff together is trying to make computers easier to use, because I think that this is the central problem, the most important problem that we're all facing, and need to come up with some way of solving it. Fortunately, computer architects have given this to us, right? So back in the old days when I got my PhD thesis somewhere over there, computers were really slow. But with all this exponential growth, AI algorithms that didn't used to work, now they work just fine. And people say, well, maybe Moore's law is dead, and we're not going to be able to keep this up anymore. And probably they're wrong, but even if they're right, it doesn't matter, because already computers are so bloody fast that we can do all sorts of things you couldn't used to imagine. So tying all of that stuff together, what I want to do today is talk about crowdsourcing, and I'll try to show how that thread fits in. And the first point I want to make is crowdsourcing is actually a super interesting application domain for artificial intelligence, and especially for AI planning. So I'll show a series of algorithms that can reduce human labor by up to actually 87%. And it's one thing to speed up an algorithm by 87%, but if you can actually reduce human labor by 87%, that's, I think, much, much more amazing. So these algorithms that I'll talk about today are really just the tip of the iceberg, because I think what they do is they represent a really exciting view for the future, and that's basically how do we make human-computer teams that can work together harmoniously and solve problems that neither humans by themselves or computers can solve independently. Okay, let me start out, since this is an AI seminar, let me start out by describing crowdsourcing a little bit more. So first aspect of crowdsourcing is going out to a crowd and soliciting effort. The second aspect is how do we combine the pieces of work that a large number of people do, even if the individual work they do is very small, how do we combine it together to a coherent whole? And finally, how do we combine it together in a way that actually yields results that are better than any one of those people could have done by themselves? There's been a whole lot of success stories with crowdsourcing, and I'm sure all of you use tools like TripAdvisor and Stack Overflow, Wikipedia. These sort of output of the crowd have really become indispensable. There's also a number of really exciting applications in citizen science, from Zooniverse, which has made a number of new scientific discoveries by harnessing, just ordinary people, or eBird, which has tracked the effects of climate change by crowdsourcing observations of migratory birds, to work done here at UW to come up with the structure of AIDS proteins and various related things. There's also a huge economic effect. I think crowdsourcing is going to change our lives dramatically. If you look at Odesk, which is now called Upwork, and just look at the growth in terms of the number of people who are working on that platform, it's quite incredible. And over a couple of years ago, it exceeded $1 billion in terms of net revenue, and seems to be growing incredibly quickly. Okay, so that's crowdsourcing. Now let's talk a little bit about AI and crowdsourcing. There's actually been quite a few papers at AAAI, NIPS, and elsewhere on doing this. And oftentimes what they do is they say, how do we take a number of simple votes of people and put them together to have a higher expectation of the right answer? Do something smarter than majority vote. This is called collective assessment. And we've seen techniques based on expectation maximization and Bayesian belief networks and Chinese restaurant processes and lots and lots of papers actually written on this pretty simple problem. And it's actually really cool research, but there's so much more that AI can do than the techniques here. So the collective assessment problem is really a state estimation problem. It's not a control problem, and it's inherently passive. But I think the thing that's really interesting is this control problem. And I'll talk about a couple different control problems today. I'll talk about controlling simple tasks, talk about controlling complicated tasks, how do we optimize workflows, talk about routing tasks to the right workers, and also talk about how do we actually use AI techniques to figure out how to teach crowd workers effectively. So all of these approaches are based on sequential optimization and sort of a formalism called partially observable Markov decision processes, which I'll come to shortly. Okay, so the overall thesis of the talk is that intelligent control and POMDP algorithms are central to the success of crowdsourcing. So I'm going to show a number of different systems today, and they all have this sort of basic paradigm where we've got a controller that's trying to figure out what action to execute. That's going to be sending some sort of actions to the crowd. So it's going to be generating a job, sending it to the crowd. Then we'll be doing some state estimation using EM and the kinds of techniques I mentioned before, and then going around in a loop. So I'm not sure. Hands? Anybody in 573? Okay. Well, you've probably seen this diagram recently, and the standard diagram of an agent and environment. Here we're having the crowd as the environment, and the real question is what goes on inside the agent's head, and that's the POMDP algorithm. Okay, so let me give a high-level description about POMDPs. I'll start out with Markov decision processes. The way to define a Markov decision process is first by defining a world state. So if we've got a simple robotic system, you might have an XY coordinate for the world state. We've got a set of actions, which could be moving in a particular direction. And since actions are uncertain because of noise in the environment, we represent them as a probability distribution. So suppose we're in a particular state at an XY position, and we execute an action, say move north, then we're going to have a probability of ending up in a number of different states. So we can think about that distribution on the right as showing where we think we're going to end up. Now, if we execute the action, then we get an observation and we see exactly what next state we're in. And we also get some sort of reward, which is a function of the starting state, the action, and the ending state. The robot was really lucky here. It might not be getting the rewards every action. Anyway, the objective here is to compute, given this is an input, we want to compute a policy, which is a mapping from states to actions, that chooses the best action that the robot should execute no matter what state it's in. So we want to maximize the expected reward, usually discounted over time, minus the cost of the actions, and that's our utility function. And then the wrinkle is, actually we want to do this while we're learning the action and the reward probabilities. And so that makes it a reinforcement learning problem. Okay, so that's a Markov decision process. Any questions? How many people have seen MDPs before? Okay, I'm sorry. So POMDPs basically take that model and extend it. So we start out with a belief state, the robot doesn't know exactly where we are. We've got the same action model. Now, when we execute an action, we get some sort of noisy sensor operation, and as a result, we can do state estimation and reduce the uncertainty in our final position, but still not necessarily know exactly what the state is. So we're back in a new belief state. We also get a reward, and we still want to do this utility optimization and still do the learning. Okay, so there's lots of different ways of solving the POMDPs. I won't actually talk about them so much. Most of them involve using Bellman's equations. And when you've got the reinforcement learning aspect to the problem, there's this exploration-exploitation trade-off that basically says, should I be trying to maximize a reward, or should I be executing some new action I haven't tried before, in the hopes of getting a better understanding, which might lead to more reward later. And there's approaches based on multi-armed bandits that let you balance that trade-off effectively. Okay, so in just a second, I will tell you how we can basically come up with a POMDP model for crowdsourcing, but let me hold off for just a second. The next thing on my agenda is to talk about the control of simple tasks. But you guys look exceptionally smart, so I'm going to skip right ahead to the complex tasks for you guys. And in particular, talk about workflows and optimizing workflows. So here is something called the iterative improvement workflow developed by Greg Little at MIT. It basically says, let's start out by asking a worker to create an initial artifact, and then we're going to send that out to the crowd and ask a new crowd worker to improve that artifact. Then we're going to take the new and the improved artifact and see, did that worker actually make it better? So we're going to have them vote which one of those is better. And in fact, we might have multiple workers vote. And then we're going to take that best artifact and we're going to go back and we're going to try to improve it again. And we'll go around this loop a number of different times until we're pretty sure we've got the best thing possible, or that we're at the point of diminishing returns, and then we'll output it. So this is a really simple workflow, but it's actually quite incredible. So if you give workers on Mechanical Turk a picture like this and ask them to write a caption, they come up with something like this. If you then send that into this iterative improvement workflow and have a number of different people working on it, then you come up with a version like that, which is a much better caption than any one worker on Mechanical Turk could come up with by themselves, even if you pay them a lot more money. Or you can apply the same workflow to a problem like this. I don't know, can anybody read this? I can actually, because I'm giving this talk. But no one person can actually read this very well. You put it through the iterative improvement workflow, and people working together actually decipher it pretty well. So this process is actually really quite cool. However, there's a number of open questions, like how many people should vote each time, and how many times should we go around the loop? And Greg, in his thesis, just used hard-coded answers for those. So for the votes, he always asked 2 people, and if they agreed, he figured that that was the right answer. If they disagreed, he asked a third person to break the tie. And then he went around the loop like 7 times, basically as much as he had money for. And that worked to get these actually quite good results. Putting this into our controller model, there's the question. First question is, do we actually need to improve this artifact at all? Maybe the description's already good enough. If so, we should just return it. Otherwise, we should generate an improved job, and when we come back, we should estimate the quality, and now we should say, we have an estimate of the quality of the 2 artifacts. Are we pretty sure which one's better? If so, we don't need to do any voting. We can just go try to see if we improve it or return it. Otherwise, we have to do some voting, and then we're going to do state estimation, update our probabilities, and so on. So again, formulate this as a POMDP. The actions, instead of being move and grasp actions, are improving the caption and voting which of these 2 captions is the best. The world state, instead of being xy coordinates, is we have two numbers between 0 and 1, which reflect the quality of the two artifacts that are present at any one time. The power used is really just the money. How much do we pay to workers? And the requester can specify any utility function that basically says how much am I willing to pay to make it better. Some people might be willing to pay lots of money to get the very best possible caption. Other people might want something that's more quick and dirty. Okay, so what's interesting about this is like a really stupid robot model. I think Dieter is cringing in the corner to even think that I'm calling it a robot. Real robots have lots and lots more parameters, and as a result, it's really hard to apply POMDPs because the state space is so big. Yes?
For POMDPs, you also need observations. What are those?
Yeah, sorry, I missed that. So the thing we observe here is some tasks, we can't necessarily observe them, so we don't actually model any observations coming back from an improved task. But if we have a voting task, then we know which the worker thinks A is better, the worker thinks B is better. That's the only observation we get. And we use that to update our probability distributions. So what's really cool is that these POMDP algorithms, which in many cases are sort of doubly exponential in the worst case, and are very hard to apply to real robotics tasks. Actually, you can apply them to real crowdsourcing tasks and get incredible improvements. So they really work. In particular, applying it to the image captioning task, what we found is using the POMDP control, we got much higher quality output than we did from using the hand-coded procedure that Greg Little used in his PhD thesis. Or if you control for quality, we ended up getting the same quality with 30% less labor, which is a lot less labor. What's even more interesting, though, is how the POMDP worked. So if you look at how many votes Greg Little's hand-coded algorithm uses, you see on average it does something like 2.5 votes. That's right, because it's going out, it's asking two people if they agree, it's done. If they disagree, it's asking a third person. If you look at the POMDP, that's what it's doing. And when Pong first showed me this diagram, I was sure he had a bug. And I was like, go back and re-implement the POMDP. But as we looked at it more, we realized actually it's being really smart, because it learned with the reinforcement learning that on the early iterations, pretty much every worker was able to improve the caption. And so there's really no point in even testing. Most of the time, it's not worth the effort. And that gives it some extra money so that later on, when it's actually really hard to improve the description, it's able to discern which one, whether something's better or not. And then furthermore, gives it extra money so it can go around the iteration loop one time farther. So it's actually pretty cool. Yeah.
Could you just briefly hint at what kind of reinforcement learning you used there?
I'm sorry, what?
Could you give us a hint on what kind of reinforcement learning?
Yeah, so I'm going a little bit quick and deep. In fact, what Pong did was supervised learning. So he had a separate process where he learned the characteristics of mechanical Turk workers. And it's the stuff I'm talking about in just a minute, where we actually are using the reinforcement learning. So that was the first work we did, and we weren't ready to try the reinforcement learning. But I talk about that in just a little bit. You know, in the more recent systems, we've done pretty simple things, usually epsilon greedy. But feel free to ask it again, since come to it. Okay, so iterative improvement's one workflow. Now let me talk about an even more complicated workflow, one for generating taxonomies. So what do I mean by this? Suppose we've got a whole set of pictures, and we want to actually, it was easy to find pictures on the internet, and we want to put them into some format that people can browse them in an easy way. We'd like to come up with a hierarchy like this, and then assign pictures of tigers under animals and pictures of people, human workers, where appropriate. Or maybe we've got a whole set of responses to a question on Quora, and we want to organize these into a hierarchy so that they're easily browsable. Oftentimes when you've got a discussion topic, this is, what are good, this one's actually, I guess, about what are good tips for traveling. You get so many answers that actually you want to be able to browse through it, and search doesn't always work. You want to have this hierarchy. So how could we crowdsource the problem of taxonomy generation? Well, it's actually really, really hard, right? Because a good taxonomy requires a global understanding of all of the data, and yet we want to have the workers maybe only see one or two pieces of data. So how can you possibly do it? Well, this is the master's thesis of Lydia Chilton. And she was actually a co-author with Greg Little on the original iterative improvement paper. So a natural thing to do was to try iterative improvement, where here you've got a taxonomy, and over here's the taxonomy. Here are the tips that still need to be categorized, and pretty cool. It didn't work at all. Okay, and basically, the hierarchy became really unwieldy, and the workers came in and they couldn't understand what it was, and they were confused about what they were supposed to do, and it didn't work. So the basic takeaway was we need to decompose the tasks into much smaller steps to make it easier for them to do. So the next thing she did was try having workers do category comparisons. So they were given a set of questions like, is saving money the same as more general than, more specific than, tips for saving money, and sort of building up a set of relationships there. And this didn't work at all. And the reason is really that without context, it's very, very hard to judge these relationships. And so the takeaway was workers don't want to compare abstractions. Workers want to compare concrete things, whether they're pictures or whether they're pieces of text. They need to have things be concrete. Okay, so the algorithm that Lydia came up with is really pretty cool. Uses Crowd to generate category names, also to select the best categories, and then to place the data into the best categories, and then it uses the machine to actually determine what the taxonomic relationship is. So let me illustrate how this works on a sort of toy example. Suppose we've got a whole bunch of colors and we want to come up with a taxonomy of colors. The first thing that Lydia's system does is it takes a subset of the data. The second thing it does is it iterates, and for each color in that subset, it asks a worker a task like this, which is, can you generate a category name? And so we get a bunch of category names. And then afterwards, we go through for each color, and we ask them, which is the best category for this color, to sort of figure out which ones are good and which ones are bad. And we get this sort of tally up there. And this gives us a filter for spam categories that aren't good for anything and vague categories that people think apply but aren't necessarily the best. And then we go through and we label the data. So you ask them for each color, does it fit or doesn't fit? Important to ask them to check both ways so that there's no lazy thing to do that's going to bias the data. You get the responses. Now we've got category membership. And so from this, we can automatically figure out what the hierarchy is, because basically we've got a Venn diagram. And we can determine both the parent-child relationships and also eliminate the duplicates. And so we've got our hierarchy. So that's the hierarchy for that small subset of data that we started with. What we do now is we recurse. So we now start trying to categorize all of the remaining colors. And oftentimes when we come to some of these new elements, we'll find out that no category really applies, and we need to go back and generate some more, generate new category things. We need to go back to the original items and see whether the original items apply to this new category, and so on. So the algorithm is actually kind of dynamic and cool, but it works. So in her evaluation, she looked at a number of different domains and measured inter-annotator agreement between the categories that her system produced and categories that experts produced, experts in this case being grad students in the information school. And you can see that the inter-annotator agreement between experts isn't that good. In fact, in some domains, Cascade agreed with the experts more than people agreed with people. Not always, but overall, it's pretty good quality. On the other hand, the cost wasn't quite as good. In some of the domains, the bigger domains, Cascade costs a lot more money. Now, on the other, one thing about these taxonomies is oftentimes you can't get an expert to do it, and so just being able to send this out to the crowd and get it done, it's parallelizable, you get it done really quickly, even if maybe it costs more, is better if you can't get the expert to do it at all. But this was a little bit disappointing to Lydia. But it wasn't disappointing to us because we're AI people. And so naturally we can come back and say, can we optimize this process? So the first step is thinking, what exactly is making Cascade expensive? It's not so much the generate tasks, but the select best tasks, we have to execute it a whole lot of times, because basically with Lydia, she was doing a majority vote of 5 workers. There's a number of initial items, a number of categories. There's a lot of jobs going out. Then the categorization step actually, again, didn't really require very much. Do we need all of these questions? Answer is no, we don't. She just asked them in a standard order. Actually, maybe there's a better order we can ask them. So coming back to the controller, basically we've got the question about which labels should we ask a human about. We send them off to the crowd, and then we, again, have to update, do state estimation, and update our posterior distribution. These distributions are harder to represent than in the iterative improvement workflow. And we've also got co-occurrence relations that we have to represent between the different labels, because basically the system is trying to build up a probabilistic model of the taxonomy as it goes. Because once it sort of has a sense about one category being more general than another, it can figure out the optimal order in which to ask people. Maybe we want to ask somebody about a node down low in the hierarchy, and then we can conclude with high probability that some highly co-occurring tag is going to apply. So this is work that Jonathan Bragg did, and he looked at a number of different probabilistic graphical models for representing this distribution. I'm not going to talk about that more today, but I will talk about the result of the controller. This is the performance of the original Cascade algorithm, and you can see that this decision-theoretic controller actually gets the same. First of all, it gets much higher performance, but it gets the same performance with only 13% as many voting jobs as the original Cascade. So now that actually brings things down where it's actually a lot cheaper than paying a human expert. So the next thing I want to talk about is task routing. And here the basic idea is oftentimes we've got a set of questions and they vary in difficulty. Some are really easy, some are really hard. Maybe we know, maybe we can predict with some sort of classifier whether they're likely to be easy or hard. And similarly, we've got some workers who are novices and other workers who are highly skilled. And there's an interesting, routing question about what should we do. So intuitively, what we might like to do is give all the hard questions to the expert workers and give the easy question to the novices, and that's going to help them build up skill. Or maybe the hard questions are so hard that the experts actually don't do much better than the novices, in which case we want to give the easy problems to the hard workers because that's really we get the performance. So we'd like to have a system which actually learns the accuracy profile, matching difficulty to skill level, and then does this allocation of tasks to workers. We actually like to do it where we're learning the difficulty and the skill level as we go. That's actually really hard, and we haven't gotten there yet. Turns out even just doing a static assignment, doing an adaptive assignment when in an online fashion, when you know these things, is pretty difficult. But again, we come back to this controller model and looking at the results of doing some natural language processing classification tasks, named entity linking. Random algorithm doesn't do so well. Round robin's a better approach, but the decision-theoretic controller does much better still. And so again, half as much labor to reach a high accuracy. Okay, so let me digress a little bit and talk about natural language processing, in particular information extraction. We've been working on information extraction for a long time, and the basic idea is we'd like to crawl the web, read news stories and other web pages, and build up a structured knowledge base of information. And I'm not going to talk about it. We've developed a number of different kinds of weak supervision that allow us to learn these extractors dynamically. One technique basically aligns a background knowledge base with the corpus, and another one actually automatically identifies new events and learns how to extract them. That's called the news spike system. And for a long time, we've been working on completely automated algorithms because in the NLP literature, that's that's what they like to see. They don't like to see humans in the loop. But it does seem natural to see whether or not we can basically take a small amount of crowdsourcing and inject it into this kind of process and get much higher results. So here, the kinds of tasks we're asking people is, given this sentence, does a particular relation hold? In this case, the alias of relation. And then what we want to do is do not distant supervision, and not semi-supervised learning, but semi-distantly supervised learning is the approach. So as we started thinking about doing this, realized, actually, there's a lot of people who are doing crowdsourcing for NLP. Chris Calliston-Birch told me he's spending $250,000 a year on Mechanical Turk. Linguistics Data Consortium has 44 full-time people. All they do is label natural language data sets all day long. So people have naturally turned to see whether or not we can use crowdsourcing, especially in the context of relation extraction. One paper by Ralph Grishman basically claims that it's much worse in expert training data, and even if you add in some high-quality data, it gets washed out in the noise. Chris Ray, professor at Stanford, and his graduate student says the quality is no better than distant supervision data. It doesn't really help at all. Much better to use database techniques and really scale up distant supervision to massive corpora. Chris Manning and Gabor Angeli basically showed there was marginal benefit. In fact, adding in crowdsourced data lowered the performance of their relation extractors unless they use a super fancy adaptive active learning algorithm they call sample.js, and then they get a 4% improvement in F1. So the natural question is, this makes no sense that they could be publishing these kinds of results. So what are they doing wrong? One thing they're doing wrong is they're still using majority vote. Another thing is they're actually not training their workers very well. They're not testing their workers very well. And they're focusing really on getting, actually they're not focusing so much on data quality, but they're certainly not focusing on trying to get just the right crowdsourcing to really have the biggest improvement on classifier performance. So currently, Jonathan Bragg and Chris Lin are looking at some of these problems and how to apply POMDP models to optimize these. I've got actually, yeah, just at midnight tonight, we've got a paper going out to NACL, and basically what we're showing is that we can improve F1 from 40% to 60% by basically doing high quality crowdsourcing data. Now, you guys, I expected you to like jump out of your seats when I said 60%. But a 20% improvement on this task is actually mind-bogglingly impressive, because usually you see like 3% improvement, 4% improvement. The fact that we didn't have to come up with a graphical model, we didn't have to come up with an active learning algorithm, all we did was like pay attention to the crowdsourcing and get really good data, and like who would have guessed? All of a sudden the learning algorithm does much, much better. Anyway, so that's kind of cool, but let's get back to this control problem. So one interesting question is, can we use a POMDP to figure out whether or not the workers are skilled? And when should we, basically, there is an interesting control problem, and that is at any point in time, you've got a worker in front of you, you could give them a little bit of training, or you could give them a test to try to find out how good they are, or you could actually ask them to do some work where you don't know what the answer is. And given that the worker is going to be staying around for a period of time and then quitting, it's not at all clear what the optimal policy is, right? You could train them a whole lot and then they quit. That's no good. So you need to figure out how to balance those three actions. And right now, what people do is they just figure, well, let me just insert 20% gold questions at every different step to make sure that the worker's not cheating on me. And this not only wastes a huge amount of time, but it lets a lot of bad workers through, and it also throws out good workers because every now and then, just by accident, they get something wrong. So this is very closely related to education models and some of the work that Travis and Zoran and Emma Brunskill and others have worked on, where, again, POMDPs are used to figure out what's the best training problem to give to a student if we're trying to teach them algebra, say. But the objective function is very, very different, because here we actually don't care how much the worker improves or how much they know. What we care is how much work they get done. And so it leads to a very different solution. So there it is. The controller has to decide train, test, or work. This is stuff that Jonathan is working on, and these are some preliminary results. And this is actually really just kind of a cool picture to put up there because it's got some nice colors and stuff. But basically it shows at any point in time what is the algorithm, what's the controller doing. And you can see it's doing kind of an interesting mix of testing people a lot at the beginning and getting them to work and then firing people. This is a simple model actually that's just trading off working and testing, and it doesn't have training in it yet. In some simulation studies, you can see a number of different strategies over time. As they spend more budget, they get better and better results, and the slope of the curve shows how good the policy is. The optimal policy is up there in red. A baseline which just has them work all the time. You get a lot of crummy workers, so you get bad results out. If you basically say, let's test them 17% of the time, which is pretty much what most NLP researchers do, then you get much better results. And when we use our reinforcement learning algorithm, we actually get much, much better results than that. In fact, very close to optimal. And so we're applying this back to the information omnivore. I'm hoping we can take some of these crowdsourcing ideas and put them together with event extraction that we're starting to work on. And and Colin Lockhart has been looking at that, and James Ferguson, and we'll see how that goes. The final thing I want to talk about is question selection in the context of active learning. So typically, what people who are using crowdsourcing to generate training data do is they try to get really high quality training data. And I've argued actually that that's a good thing. But it's not clear that's the optimal thing. In particular, there's kind of an interesting question that nobody has looked at, and that is, suppose you've got a fixed amount of money, and you don't care about the data quality. What you care about is having the best possible classifier that comes out of it. In that case, how do we solve that decision problem? So suppose we've got $9 and we've got a whole bunch of images that we want to label to build our image classifier. Then what we could do is we could do unilabeling, assign one worker to label one image, and then we're going to get 9 labels. And if the workers are 75% accurate, we'll get 9 labels that are 75% accurate each. And that's maybe good for our learning algorithm. Alternatively, we could do majority vote, in which case we're going to get 3 labels, and each one is going to be 84% accurate. Or we could just get one example, and then we can get 98% accurate. And so, which of these strategies is the best one for your classifier? It's not at all clear. So one thing we did is we actually started looking at some existing data sets to see what strategy might work, and that's what we got out. We got basically, in a lot of domains, unilabeling was the best strategy. In a bunch of lanes, you wanted to actually relabel, and these are different relabeling strategies with different amounts of redundancy, and that actually worked much better. So it wasn't at all clear. Clearly, there are some characteristics of the domain that that affect this control problem. So Chris Lin has a nice paper at HComp a year ago that basically looks at the factors of the domain that affect the correct policy for doing relabeling. And we identified 3. One is the inductive bias of the classifier. Another one's worker accuracy. The third one is the total budget you're willing to spend. The most interesting one is inductive bias. So the basic idea is if you've got a strong inductive bias, then you've got very limited expressiveness. And in that case, actually, unilabeling turns out to often be the best strategy. Or maybe you've got a really weak inductive bias, so you've got a classifier which is very, very expressive or a very high dimensional feature space. In that case, it turns out unilabeling is really bad because it leads to overfitting, and you want to do some sort of relabeling approach to get more accurate labels. And the actual correct policy is really kind of tricky. And of course, you probably don't want to have a uniform policy for all of the examples. Some examples maybe matter more than others. So that leads to kind of a cool problem, which Chris calls reactive learning. So it's basically active learning over traditional active learning is, given a set of unlabeled data, let me pick one point of data, which is the point that's going to give me the best improvement to my classifier, and I'm going to assume that the label I get out is right. So there's no point in ever doing it again. But here, what we really need to do if annotators can make mistakes is choose not only the unlabeled data points, but also previously labeled data points. Maybe what we want to do is go back and relabel something. So you might try a strategy like uncertainty sampling, which is a standard active learning approach, and it doesn't really work. It oftentimes loops infinitely and then starves a bunch of data points. Naturally, it's a controller. What Chris came up with is kind of a cool strategy called impact sampling, which what it does intuitively is it says, if I was to label this point, what's the expected change that label might make to my classifier? And then it's going to choose to label the point which has the highest impact. And That's a myopic strategy. It's only doing one step look ahead. In fact, you'd really like to do multi-step look ahead, but that's combinatorial, and we don't really know how to do that. But Chris came up with something called pseudo look ahead, which allows you to actually get much of the benefits of a look ahead search without having to pay the costs. There's an interesting question about whether you should use expected impact or optimistic impact in terms of what the probability of the label that the annotator is going to give you. I think it makes complete logical sense to me that expected impact makes more sense. Unfortunately, optimistic impact works a lot better. And somehow Chris and Mossam have convinced themselves that that actually makes more sense too, but we keep arguing about it. Anyway, here you can see that we do much, much better. So this is the number of labels, the annotation budget, and you can see that on the y-axis, you've got the accuracy on a held-out test set, and you can see the green curve, which is impact sampling, really does much, much better. So it's pretty good. We also, the one weakness here is that this is simulation experiment. So when we tried it on real data, we got some good results, but the results weren't as positive as we'd seen on the simulated data. So that was a little bit frustrating. But Chris has a nice paper on this at AAAI in a couple weeks. Again, some other studies on real data. It seemed to help a fair amount on the relation extraction task, but not so much on the Galaxy Zoo task. Okay, so let me wind it up. One thing I want to say, that I probably said, so Ted said it sometimes, POMDPs are really a great way of taking crowdsourcing and getting much, much better bang for your buck. And the controller can ask all sorts of questions like, what should I ask a worker to do? How many times should I ask them? How much should I teach them? Who should I ask? Should I test somebody? When should I stop? There's a couple different objective functions, including getting high-quality data or just trying to get a high-quality classifier. And then the bigger point is that I think trying to use decision-theoretic control of crowdsourcing is our first steps towards coming up with these teams where computers and humans are working together, and computers are partly tools that the humans use. They're partly agents that are contributing on their own right, and they're also maybe trying to manage tasks as tasks get distributed between different people in the team. And then backing up one step further, the vision is how do we use AI techniques to make computers easier to use? Anyway, that's it. Thanks very much.
If for an experiment you want an interlabeler agreement, how would you put that?
I'm sorry, can you speak up? Say it again.
For an experiment, if you wanted the interlabeler agreement, how would you mix that into your whole system?
I'm not sure if I understand the question. So you're trying to, what's your objective?
So let's, so I understand, so I think it's really cool that here you can get better and better labels because people are kind of learning from each other. But say that for an experiment, it's also important for me to see what the natural interlabeler agreement is. So how do you?
I think in general, since we are usually collecting multiple labels from different people on the same examples, you can compute the inter-annotator agreement sort of automatically out of this. If having a high-quality estimate of the inter-annotator agreement was important, you could put that in the objective function, and then the system would go out of its way maybe to ask the same question multiple times to try to decrease uncertainty in the estimate of that variable. Yeah.
I was going to ask, one of the first things you were describing was the voting, and instead of doing this best or majority vote, you would do improvement and things like that.
Right.
And it struck me as like human loop optimization or something, right? Where you have this problem where you want this thing to get better over time, and you put humans in there because they're good at evaluating these things. But I wonder do those techniques come from more traditional optimization settings, or is that something that someone invented specifically for this problem where you have humans doing it? And would that be possible to kind of like extend that improvement voting into situations where you had maybe a bunch of possible AI workers that were operating these things?
Yeah, absolutely. So in this case, in most of those tasks, all of the workers out there were human workers, but there's no reason why those workers, you couldn't have a mixture of AI agents out there as well, and the system would be passing questions off to them as well. Typically, the cost of those agents is much less than the cost of people, and so it's almost free compared to the cost of people. So a good strategy in many situations is just always ask the computer agents first, and then based on their information, decide whether you need to ask people as well. And H.A. Kamar at Microsoft Research, who's done a lot with the Galaxy Zoo data, has done strategies like that, where they basically always run the computer agent. If the computer was so computationally intensive that maybe it was better to ask a person than ask the computer, then that would fit really naturally into this framework. You just say, well, how do we balance off the cost of asking a human versus 2 hours of computer time? And then the system would automatically figure out which one it should ask based on its estimates about the accuracy. Any other questions? Yeah.
So in the last example, the performance on Weld as a data set was a much smaller improvement. Were there any data sets in some of the prior methods that you covered that you had kind of disproportionately poor performance?
That's a good question. Chris, were there any real-world data sets where reactive learning, make sure I've got this question right, are there any domains where reactive learning did especially badly?
Not especially badly. Perhaps a little bit worse.
Yeah, I guess my question was just kind of overall through the methods in the presentation, because I saw some variability at the end, and I was wondering if there was more variability early on. Because there's lots of different data sets we can all look at. And I can imagine the performance be very different for different kinds of tasks. Like the image labeling task is one where you're generating a potentially really long string of characters. There are other ones that are much shorter, versus like picking a category for something. So I was curious if there were any patterns there that you guys had.
Yeah, I mean, just speaking of patterns, I did skip past one thing. It turns out that all of these examples are very low dimension. They're like, 20 dimensions or less, and these are all really high dimensions, right? So it fits naturally into that category. But of course, any learning algorithm is going to do well sometimes and not well other times. I want to close by thanking my wonderful co-authors and thanking you guys. Appreciate your coming, and we'll see you next week. The talk next week is going to be Carla Gomez from Cornell University, and it should be super great. And look forward to seeing you then.